Okay, so we were doing cat file one with redirection, and so we can see that we've made a file. We can look at the file. We can put the content of file one into file two. And I was just going to comment that you don't actually need to put the one here. This will have the same effect. Well, let's look and see. File three is this, but if we do cat file one into file three without the one, it still gets file three has now become file one, or the content of file one. So they don't differ. Now, but the thing is, I could also, now, I could also do two here. However, two is standard error, and cat, unless it has an error, isn't going to write something. It may be that if I do, let me see, let me make sure there's no file. Okay, there's no file. So if I do cat no file, it does this. Now, does it send this to standard output or standard error? Let's see. So we can do is we can do two. We can redirect what's going to standard error into error file. If error file doesn't exist, which it probably doesn't, the shell will create it in order to do the redirection. Okay, so let's see. Cat error file. So it does. So what it looks like when you give cat a file that doesn't exist, that it sends the error message to standard output, but it doesn't. It sends it to standard error. So so therefore that way, if you have an application that has an error, you can save those errors to a file or change the output. This is behind when we did strace on say PWD. strace sends its output to standard error, right? The PWD sends it to standard output to file descriptor one, so they get mixed up. So if I just do this, I have in here, so I have this weird thing in here where I have the right home var, then I have, so this home var here on the right, on this line here, was due to PWD, but this one, the first one, was due to strace. So usually I want to separate those two, is separate one into, this is a device file that you can write it, you can write all you want to it and it just forgets. It's like an information black hole. Okay, so if I do this, then I get this line here without the confusing output of the standard output and standard error getting mixed up. So it's easier to read the strace here. Okay, so that's redirection. But the question is, how is redirection implemented in a program? Well, let's look at how that works. See if we can find a data flow diagram. Okay, so what happens is this. Let's say maybe I need one with two. Do I have one with two? Maybe I need a different one. Let's see, where would that be? Okay, here's one with two processes, because what we're going to have is we have, say, the bash shell running over here, right? And so it has 0, 1, and 2 open, right? And 1 and 2, let's not worry about number 2 right now, but number 1 goes to the terminal screen, and 0 is connected to 0, and it does stuff. Now let's say that I then want to do one of those redirection commands. What it's going to do is, see, it's going to do two things. It's going to fork and exec, right? Just like your M, this happens in M shell. So when you fork, this could be M shell too. When we eventually implement, when you implement redirection in your shell, your M shell will do the same. This is the behavior that you want to reproduce. Okay, so bash will, what it does is before, it's going to fork, right? When it forks, it's going to create here, say, cat file. Let's say I'm going to try to put the whole thing up here. F1 goes into file 2. Okay. So how does it implement this redirect? Because the shell is the one that does the redirection. Well, when it forks, it clones this. So initially, what I want to do is the cat program. But initially, what I have is I have a second copy of bash running because after fork, right?
Yep.
Okay. But now but then it's going to have the same file descriptors, right? Like this. But now in this shell, we're going to call exec, and we're going to call exec with say cat file 1, say 1 goes to file 2, right? So usually but cat can only write to file descriptor 1. It can't open, in other words, it opens when it writes something. When how does it do this? Cat has to open file 1, but it's going to write to file. It doesn't know about the redirection. So it's going to open, when you exec, it's going to open a file. It's going to open file 1 down here that will get file descriptor 3. So there'll be a connection up here, which I'll do in a second. But first, what the shell does, it has to set up the fact that cat will only write to file descriptor 1. It doesn't know about the redirection. So the only thing that the shell can do is close. What it does is it closes 1. So that erases this line here, right? So then file descriptor 1 is now unused. Then it's going to open file 1 for reading, okay? Well, then you're going to get this line here, this pathway here, meandering around, going to file descriptor 3, right? So then the code, then cat will be reading and then writing, but what it does is it's going to write to 1, right? But then this isn't what happened. This is what usually happens. But what actually happens is because this is open, and because open always gets the lowest unused file descriptor, when you call open, it goes to 1. So now when cat no, what am I doing? Sorry about this. I was actually right. We need 2 files. Sorry about this. We have file 2, right? So what the shell does is, let me go back. I jumped the gun. So we haven't made the file 1 connect. So we're going to close 1, then we're going to open file 2 because we want to write to it, right? But we're going to open it for writing. Sorry about this. Let me get this straight. Should have. Okay. here's what we need. We need to be able to open file 1 for reading, right? And open file 2 for writing. But cat can only write to file 2, right? So what we need to do is we need to close file 1, then open file 2 for writing. So we close file 1, then we open file 2 for writing. Which, because 1 is unused, it gets connected not to, let me get this out of the way because that's misleading. Sorry about the confusion. So you've closed file 1, then you open file 2 for writing. And what's going to happen is then file 2 is going to be connected to 1. So when cat writes, when you do exec and you write to file descriptor 1, instead of going to the terminal, it's going to go to file 2. So then you can open file 1 for reading. And so file 1 will get the usual file descriptor 3, because cat can read from file 3 and go to file 1, right? So what has to happen is, what you have to arrange in the shell for redirection is a little complicated, right? Because you have to arrange for file 2 to be opened on file descriptor 1, because you want to write to file 2, and then you don't want to do it in the wrong order, because if you do it in the wrong order, you might end up, if you closed 1, then open file 1 first, you'd end up with file 1 where you want to read on file descriptor 1, and then cat would try to write to it and it would fail. So you have to be, so the order of these things matters, right? So you have to close 1, yep, open file 2 for writing, because that gets you with file descriptor 1 because you just closed it. And then you can open file 1 for reading so that cat can read from 3. So cat's the one that wants to open this one. But this stuff here has to be done in the shell, right? Because cat only knows how to open file 1. This is cat here. It's the one that knows. So the point is that the shell has to take file 2, close 1, open file 1 for writing, and then you end up with this diagram. Now, the shell doesn't need, because the child is going to write to 1. Anyway, you've got this complicated thing so that then once you've, say, closed and opened, and before you've done this, before you've closed, what happens is you've called exec, right? And cat is running here. And so that you do this stuff here, then you do exec, because that exec runs cat, which replaces cat in this process here. And replacing the program doesn't change the file descriptors. Exec, the file descriptors in the process, what you've done in the shell in the child remains there. What the exec does is just replaces the program and the memory, but it leaves file descriptors alone. So if you've done this plumbing, it doesn't change the plumbing. So that way you've got this complicated scheme that allows you to do redirection. Okay, so this is what's going on in the shell.
Okay, and when you finish concatenating from file descriptor 3 to file descriptor 1, that disappears and your plumbing goes back to normal?
Well, no, the plumbing is normal for the shell.
Yeah.
Remember, when cat completes, this process exits and disappears.
Yep, that's what I was asking.
You close 3, and when you exit, all these get closed too. So all this stuff, all the child lines disappear, and the shell, the bash shell, which is called exec, which is in which you've in the pair after the fork, there's an exec over here in bash before calling cat, and then over here you've called wait, right?
Yep.
So the parent is waiting. And so then when this returns, then the shell goes back and gives you another prompt.
Okay.
Okay. So this is why the data flow this is why or one reason why when you've done the earlier data flow diagrams, I've required you to be precise and taken off points for various things, because while it's not so important for doing just file input and output, it is important when you want to use these diagrams to understand redirection. And then we also have to use these diagrams to understand pipes, which involves even more plumbing, work, because we have to sort of close and open multiple things. And there's some new system calls, dupe and dupe2, that duplicate file descriptors. So we have multiple connections because we don't want to forget one. Okay, so this is one thing. And if you notice, for example, this is what's happening here in this one here, that let's look at this mystery program, see if we can understand what's going on. So if there's no fork here, let's go and here, I'll export this as something. Then we will annotate another one. Data flow 1. I think we just want one. Okay, so we just have one process here, right? So when it starts running, when mystery zero starts running, by default, open pathways 1, 0, 1, and 2 are open, and by the way, these two lines connect at the hardware level, not at the software level. These are two different pathways that will have different, so they don't connect at the system interface user space line. They connect here at the hardware line. Okay, so mystery 0, this is the default. We close 1, okay? What does that do? Well, that erases this line here. Okay, then we open storage 0. And what storage 0 does here is this is its use specifications. This one here means we're going to write. This one here, the far right one. The 100 is created if it doesn't exist, and the 2000 here, 200, is append. Now, usually the way you see these if you saw this without these numbers, where this number would come about is from probably a bitwise OR of O, I think it's O, append, bitwise OR, O, create. For some reason, they left off the E. Dennis Ritchie said that was the biggest error he'd ever made, was to leave the E off of create, because it's the only word that's like misspelled, so to speak. We thought it was too long. Like he didn't want 6. Anyway, so much for that. And then read only. Well, if this is the number, the binary number, let's do it in, let me see. Well, this is octal here, right? So this is the number 1. This is the number, let me see. It's going to be the number 001, 000, 000, right? So we could say this is octal. So it's really binary, right? But then it's reported as octal 100, and this would be, to give it the same number of octal bits. This is like 0, 0, 0, 1. I don't know if you can do this. You have to do a 0, but then append is going to be even more bits. It's going to be 0, 1, 0. That's the 2, and 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is then 0, 2, 0, 0, 0, because each of these octal numerals is 3 binary numerals. So when I do bitwise OR, these ones are all in different slots. So when I do bitwise OR, the binary number I get is 0, 1, 0, 0, 0, 1, I think, 0, 0, 0, 0, 0, 1. Okay, Phoenix. Oh, yes. It's sorry about that. It's write only. Yes, read only would be all zeros. This is write only. Okay, so this is what if you look at the actual official source code, or if you did this for real if I wasn't forcing you to use these numbers, so you understood what's going on, you would write this long thing. Of course, it's easier to write 0, 2, 1, 0, 1 than this whole long thing here, but you'd probably just copy these in from, use your typical mouse crutch, so to speak. And so anyway, so if I do the bitwise OR, I just get what it means is I'm getting all these properties at the same time. So if I want to add a new property, I can just bitwise OR that property. Okay, so if I look, when I do man open, man to open, I think, and I go down here, see here's all of these ones. Here's like read only, write only, read write. Like this is 0, 1, 2, right? And this then there's O directory, truncate. You can add in if you want to make sure the file gets truncated. You can do O append. And there's other ones that are have to do with the fact that many of these programs can be run in circumstances where there's more interference that can occur on a server if it's very busy. So you have to be very careful about the input-output stuff. So asynchronous can all these things are useful, like especially with networks where there's timing issues involved. And so, we don't have to worry about any of that. So that's why the actual code is more complicated than our programs are really simple compared to that. Okay, then there's all kinds of other things, and each one of these options has its own stuff. And then there's also, these are the permissions, all these permissions I've given. Well, there's all these little macros here, these definitions for, let's see, read, write, execute, user, read, user, right? This is write user, execute user. So there's a whole bunch of these that sort of all the different possibilities of, and they show you what the octal permissions are for these ones here. So that in the code, if you want to give permissions, you could just glom these on like that. And there's other ones too that have special technical, and there's all kind, and you can read about what all these are, but there's zillions of, some of these are suggestions like large file. Anyway, there's all kinds of special circumstances. But anyway, but the point is to realize is that these are bitwise OR allows you to glom on lots of properties at once. And it's all because one of the things for sure, each of these things is a binary number with only one bit, everything else 0. They're like masks. They're just this special, and that's probably how they're used inside the program. They're used as masks because once you have this number, you can like use it to select out the properties you want to cause the program to act the way you want. So here we have opened the file for writing. We create it if it doesn't exist, and we're going to write to it by appending it, so we won't erase what's already there. We'll just add it to the end. And probably that's done by lseek. You know, the program will either start at the beginning or it will lseek to the end of the file and start writing there. That's how you could implement the append doing that with your code itself. Now here, then if you do create it, here's the permissions. The user has 6 is, you know, the octal read write, and this is read write. So the group has read write, but the other people don't. Okay, so and of course that's a security issue. You just think, you know, you don't want, you know, 666 is evil, right? So okay, but you create, so therefore
depends on your background.
It depends on your background. I guess I shouldn't say that. If I offend you, I apologize.
No, I'm not offended. Just
well, someone else might be. There was someone who was offended one time that they were really bothered by that, so I had to take it out from various portions of the course. Okay, so so we've closed one. Getting back to the actual stuff we're supposed to be doing, you close one, then you call open. Well, it's going to get the file descriptor 1 and connect that to put the kernel buffer in here, and you've opened it for writing, so you can put the arrows on, okay? So then you've opened it, so now you have it set up. Then you call exec, and we're going to run another program, right? So then mystery 0 will no longer be running after exec, and it's going to run hello 42, right? And hello 42 is this mystery 1, mystery 0A. Here's 42. Okay, so all it does is it printfs this. It just prints this program. It just prints hello world. Okay. So it doesn't know anything about redirection. It just knows printf, and printf writes to file descriptor 1. So what's going to happen is, though, in here, hello 42 is going to call printf, and printf is going to write to file descriptor 1. It doesn't know that it's connected to the terminal. That's the important thing, is when you call printf, it just writes to file descriptor 1. It doesn't know where file descriptor 1 goes. It's like file descriptor 1's a loading dock on the program, and printf just loads up the bytes on that loading dock, and a truck comes and hauls it away, and the shell is redirected where the truck goes, to a different road. And that's what's happened here. So then hello world's going to appear in this file down here rather than on the terminal screen. Okay, so I think in this series of programs, we will be completing a fresh data flow diagram for several of these mystery programs. There'll be 5 diagrams. So in this mystery activity, you're going to write 5 data flow diagrams to illustrate, to sort of carefully show the this redirection, where you will show the final thing. In other words, what you'll be doing is showing, like this. You'll be showing, okay, hello 42 is running, and this is and we don't know what's going on inside. All we know is the external stuff that's going on. Like here's a different kind. Here we close 0, right? Well, 0 is only connected to the keyboard. Then we open storage 0 here and use some other stuff. So each of these programs has a slightly different data flow slightly different redirection. Okay, that's what I wanted to. So in other words, this is sort of like different. So even though this is like next week's stuff, you can start it now if you're thinking, or it might take a while for you to sort of digest what's going on, because once you understand redirection, then when you go in to do your MShell stuff, because I don't give you the template, I give you the ideas, but I don't give you the code for implementing redirection. So this goes back to you having to do a little more programming, and the previous sort of improvements have been relatively simple, right? You write a function for MCD, you insert signal, you insert system calls various places, but this requires you to actually do a little bit more. And also you might have to reorganize the MShell code a little bit to decide where everything needs to happen. So you have to understand it a little bit more clearly. So that's why you might not want to just do it at the last minute. You might want to sort of go through and pay attention to this first one, which is activity 8, which is the mystery programs, which all involve redirection of various forms. And then the next one is adding redirection to the shell. And see, this is how we haven't done, I think, redirection of file descriptor 0, the keyboard. So this redirects the output of what command writes to file descriptor 1 to file 1. This gets input from file descriptor 0 and sends it to the command. So you see the arrow, think of this less than symbol as pointing from the right to the left, like it's a little arrowhead. And you can do both at once. Like, for example, let's say we have, let's see, cat file 1. Okay, so it has a quote in it. I got this, so cat file 1 has like there's a program fortune, right? It prints off fortunes. So I made this file 1 from this. Well, what we can do is, let's see, cat file 3. Well, that's not very interesting. So let's try cat from file 1 to file 3, right? This should, if it all works correctly, read from file 1, which is this epigram up here, and writes to file 3. Let's see. Then we can do cat file 3. So it did it. So this was using input and output redirection. So that's what your shell, you want to be able to do on your shell this and have it work properly. MCAT, you're going to have MCAT 0 here, right? All that does is reads from the file and writes to standard output 1 byte at a time. It doesn't know anything about the redirection, so this has to all happen in the shell. So that's the project for this stuff, and you can see that there's a little bit more. We have a struct that remembers stuff. Okay.
So cat does not read from standard input, right?
No, cat. Okay, yes, cat does read from standard input. When you see, usually what you do is this. Here's the deal. This is the thing we didn't implement. So MCAT 0, you probably need we need a revised version of MCAT 0. Probably doesn't work with MCAT 0 the way we did it, but so if we do cat file 1, it reads from file 1. But if I do cat, then I do this is a note, and I do, see it echoed it back. It read from file. So so I typed, this is a note. Cat read that. When I pressed enter, it sent it to standard input. Cat was reading. So when you press cat with no file, it goes, instead of open, because there's no file there, it goes and reads from standard input 1 instead of 3. So you could see how you could implement that very easily in MCAT. Okay, and then you do Control D, stops the input. Now it works also with dash, right? This is another note, right? But the point of the dash is that you might want to do file cat dash file 1 dash file 3, right? File 2. Then I could say, okay, this is an epigram. Oh, no, that didn't. Oh yeah, then I do. It should have. Okay. Oh, okay. Let me start again because it's going to be confusing if I don't. what I want to do is send everything to list, right? Maybe list is a bad, let's see, file list, okay? So then I do, this is an epigram, Control D, then this is another epigram, Control D, then I do cat file list, and you say, this is an epigram, there's one, this is another epigram, which is a lie, and I get the second file. So what it allows you to do is intersperse comments that you've put in, then something from a file and something from a file. No, okay, for you, that's not very, for a user, that's not a very, like, you could ask, why would I want to do that? And the point is, Bash is a system administrator's language. All these utilities are, yeah, they help you to move around as a developer, and they help a system administrator to administer their system. And so these things are useful in that context because you might want to automate your system. And because you're then, Bash is something that runs other programs. It's similar to pcheck. Originally, pcheck was a Bash program in which I had Bash run various programs, and I needed to manipulate standard input, standard output so I could then check it. Python is much more effective for that, but I'm doing the same thing. I'm calling, like I use like grep, right? Grep is a command that looks for, like I could look for this in file list, right? Well, there it shows that there is, this shows that in this file, this string does occur, right? So maybe I want to do various things to search. Like I was choosing the original pchecks when they were Bash checks. I would compare stuff using like your output file. Did it contain this string? It's much easier with Python, but Python does the same thing. I can still do similar things. Okay, so that is some of the stuff that you can do with sort of the context of where all this stuff is coming from, why you have it. So the original context was, why would you have this? The problem is you have the cat is sort of a short form where you don't have to put the dash. But the problem is that you can't put, because spaces are used between the files. If I wanted to do this, I have to have some other way of say dash. This means get it from the command line, get it from the keyboard, get it from the keyboard, right? The dash means get a file from the keyboard, the sequence of tokens, characters, the user types, get the next file from file 1, from the keyboard, from file 2, and then redirect everything to file descriptor 1, which is redirected to file list. Yeah, it gets from file descriptor 0. Every time you give cat dash, it gets it from file descriptor 0. So it's like that is, dash means the file that's coming from file descriptor 0, and the no dash feature is just sort of a convenience. For example, if I do cat dash, it does the same thing as cat. In fact, actually, I have been preparing a replacement project for those early file projects that involves writing a version of cat that's different than the version that you wrote for MCAT 0, but that includes more stuff so that you can, if you had issues in those early projects, you can do that. So we will have another, hopefully it'll come live this weekend and it reviews a lot of this stuff. It starts off with a version of cat that does some of this stuff so that it sort of reviews
hey, good morning,
the spirit of the ideas that I've been trying to get across.
Professor?
Yes.
So if no one has any other questions about that, I just have a question about the data flow diagram.
This one or a different one?
One I'm working on. I'm just curious, where does printf come from? Because it's technically from the program. So would that mean it's just it's a function of the buffer? or what that program terminal that you have open with the 012?
You mean, oh, what do you mean? You mean this one here?
Uh,
Oh, you
so
have,
I'm working on mystery one.
okay, so you are working. Okay, so the point is this. This is the data flow diagram for mystery one, right?
Yeah.
Because printf is a library function.
So I just put printf in the.
No, you're not animating the program.
Okay.
You don't have, for these programs, you don't have any buffers in here because we like.
There's no buffers being used. Yeah.
Well, let me see if I can make it more. Where is elf map? Is that it? Oh, maybe it is. Okay. This is somewhere in the text, right? So behind, this is what the memory space for a process looks like, right? This is somewhere in the text. You've probably forgotten it.
Yeah, I remember seeing it though.
Okay, so here's stuff from reserved for the kernels, right? See, argument environment. There's probably somewhere there's like the file descriptors for the program, and you have a stack of frames that's scrolling down, and you have a heap, and you also have data. You have your program down here, and you have global. And you have global static variables down here. Well, so your printf statement is a library function that probably gets the hello world from the text segment here. So it's in read-only stuff. And what it does is it writes it to probably some place in the heap. It probably has buffers in the heap. So when you, in principle, but you don't have to know this, in principle, printf is going to have in your process a buffer in the heap. Okay, so what printf does is it writes to this buffer.
Okay.
And so then what's going to happen is then your program at some state, printf is going to write to the buffer. Then at some stage, it's going to get written to file descriptor one. But
Yeah,
maybe
because
not right away. Maybe it's going to wait, until maybe if you don't do a new line. I think if you do a new line, it sends it to file descriptor one. But if you don't, then it will wait in the buffer. So sometimes if your program closed too early, that's when you can lose stuff. So this is a user space buffer that's in your program. It's in the heap. This is a kernel buffer that has to do with the mismatch between the fact that the hard disk is slow and your program is fast because it's running on, it's an electronic program running on a motherboard, it's with fast electronics, and this is a physical device oftentimes that's much slower, even if it's an SSD drive.
Okay, so
for this program, there is a buffer, right?
Yeah.
But where it's getting the text is from the program itself, read only. So it's probably a pointer to that thing in the program, and then writing it. I mean, I don't know for sure, writing it to this. Well, you don't need to put in these programs unless there's a buffer. You don't need to put anything inside. We're only concerned with the plumbing of the pathways.
Okay.
I don't know if that's universally true, but I think for most of the most of the mystery programs, you see here, there's just open, close zero, close one, open, and here you open some things in the child, some things in the parent. Close 0 and 1, you just do different things. So each one, there's no buffers you have to worry about. None of these are, if anything, these are only using kernel buffers. Except the first one, which uses printf, which you can ignore. So you can ignore.
So I don't need to add the.
No, you don't need to.
Can I share my screen, just so you can see how I did it?
Okay. Feel free to go. It's 10:52, so we're minus 620 seconds, right? Okay, so your program, does it write something to the standard error? So the idea here is don't show things that aren't used, right? Because we want to know, yes, so what happens is this. So you don't need the printf and the hello world with the buffer thing, right? You just want, and you want the program up top, like what program is running. You can zoom in too, by the way. You can type, and you can zoom in, and then you can use a smaller font and you can use the T to like type. Let's see if you put in the right name of the program. Oh, and you just missed it. That's not the right name because that's not the program that's running. At the end of the program, it's hello world. See, you call exec, right? So here, you see, you call exec and you're running hello 42, right? Exec takes out mystery 0 and you're running hello. So you can tell that if you, after this program concludes, when you're doing 0, you can ask, well, what's echo $? Because you're going to get either 0 or you're going to get 42. So you can check, was hello 42 really running at the end by doing echo $? And the same thing with this one. I'm not sure what the difference is. Oh, this is using printf directly. So these are really just showing you, this is a little, if you're doing 0A, it's going to be mystery 0A, right? But if you're doing the first one, it's going to be hello 42. So that means that and you don't put the C because what's running is not the source code, it's the executable. And why did you capitalize the word mystery? That's like the kernel's not like a person that can likes capitalized words. You want to maintain control over your also, why did you change the name of the file? It tells you exactly what the names are in the document. So you don't change the names and you're going to add. So look at the document and it's going to, I think don't I tell you the names to put in? I might not, I might have blown it and not told you the names to put in, but they're on the right. I can't see quite. Yes, let's see. With one page for the on your work, putting these pages together. Okay, well, yeah, maybe you do need to put the, okay, so you'll put mystery, that'll be okay. Put mystery 0A, then your initials after the program for the file when you save the file. Not in there, that's mystery 0A, but you'll put for the file, you'll put for the PDF, not the C code, but the PDF that you export from this, you'll save that as mystery 0A WD. You can always save it again. Okay, but you know what I'm doing. I think all of those things are instructive exercises for everyone to follow, so you know what the file names are and stuff like that. Will, is that good? Thanks for letting me,
Yeah, sorry, I was muted, but now I see what you're saying. To put my initials at the end of the data flow diagram name.
Yes. And then because you already give, and then when in the diagram you put the name of the executable, and then you'll have your source code problem. You have sort of the data flow diagram that represents the executable. You have your source code program, and then you have the data flow diagram PDF name.
Yep. So,
and don't capitalize the M's in mystery. It's like, it's, as a developer, you have to maintain control over the as a user, it doesn't matter of applications, but as a software developer, you have to maintain control over file name
syntax.
file names. For me, for example, when I say I have all your files and I want to look at them all in one directory, that means they all have to have different names, and I want them to be sort of alphabetized by your initials. So that means that if you put a capital M and somebody put a lowercase m, either they're going to be disorganized, or I have to go through and change all the capital M's to lowercase m's.
Mm-hmm.
So
And it says you want them all in the same PDF. How do we stack? How do oh, okay. Now I found out how to duplicate
PDF arranger, right?
Okay.
So yeah, there's a whole thing where there's like you could have the PDFs, right? Or you can have, what do I say? What is the directions we're looking at?
Draw them precisely and carefully.
Let me get it up so that this is for next week. So this is not
also, you're not sharing your screen.
Oh, yes, okay. So this is something that we will repeat next week. So this is not like to be worried about now. But the point is here, complete this activity by combining the 5 annotated PDFs after exporting them from XJournal++ with PDF Arranger, and submit one PDF with the 5. So it doesn't actually matter what you name the 5 PDFs, because you're not going to be turning them in. Submit one PDF with all 5 completed data flow diagrams. Each they'll be on a separate page under the name Data Flow Mystery for You WD.pdf. Does that make sense? PDF Arranger
Sorry, I was muted. Yep, it makes sense.
It's because in here you have PDF Arranger down here, and what it allows you to do is you will add a file. Like you'll find each of the PDF files, right? And you'll add them here. Then I think, zoom in.
Can I share my screen really quick?
And here there's one that once you get them, you can print them out as export selection. Once you have it, that way you'll have all the 5. You'll have one document to turn in.
Yep. I found another way to do it. So what I'm doing here is I just duplicated each page. So I duplicated each page, and then I can just write on each one. Does that work? So say for instance, this is
so scroll down. You have I want to make sure that you have, yes, that would work too.
Okay.
Yeah, you could duplicate each page and then have one document with the 5, and then you would avoid having to use PDF Arranger.
Yep.
So that's a good idea. Do remember to use export, because what happens is that when you annotate it, the PDF is only the background. And if you save it and you send it to me, my background won't be there, and you'll just get the stuff you wrote with no background, which is impossible to understand. That's why you have to want to export the document that you've annotated rather than just save it or whatever. Okay. So other questions? Feel free to head off. It's 11 o'clock, especially if you have other classes. This is all for next week. So this was just a preparation for, we don't have class on Friday, by the way. There's no class. The demonstrations will be opened on Thursday afternoon.
I have a question.
Okay, Yunjin.
Can I share my screen?
Yes. Oh, we have a lab today.
Yeah.
Forgot about that.
I trying to do MShell 7.
Okay, now what have you, let me see, let's see. Okay. Here, I have one, here's something. Let's see. Let me get, this isn't what you were asking about, but I want you to do one thing. Run MShell 6, okay?
Run MShell 6.
MShell, is MShell 7 is now pretty much MShell. Well, run MShell 7. Run MShell 7.
Yep.
Okay, now type in here, let's see. Oh, no, don't do this. Exit this. Okay, now type in here junk.
Junk.
Yeah, it just, okay. Okay, now type echo $ question mark.
Question.
See the number that gets returned? That's the return code of what the previous exercise or the previous bash returned.
Oh.
Your program should return that same value.
Oh.
Okay, so you fixed the immediate, you've done the immediate fix except for the code.
Yes, no.
Oh, and then also for MShell 7, you don't need lines 33 and 34, right?
33 and yep.
You can comment those out or just remove them for MShell 7. Okay, so now this is before. So your question is, what is your question?
So when I do this one, it say it shouldn't line in 36. It shouldn't.
36. Yes, it shouldn't have all that stuff. That should be okay. You need to not only comment it out, you need to remove it.
Just remove it, everything.
Yeah, remove all that stuff.
Oh, okay.
That's what it's. That's what. Now save that, and it's probably will fix.
$19.
Yeah, you still have you have to get rid of all those variables.
And just.
I think command status is in there. The
Yes.
remember the you have 2 lines there that need semicolons. Okay, yep. Now try that. Did you check the return value of a bad command?
Maybe 160 to this
one. Okay, now try.
Oh, thank you.
So you got, let me see. Oh yeah, so MShell 7's you're done. And you can see how I tested it, right?
Yeah.
Okay.
Have a nice day. See you.
Okay, take care, Yunjin. We'll see you later.
Bye, Yunjin.
Bye.
Christina, you got a question? For what?
Name 3.c.
Name 3. Oh, name 3.c. Do you want to share your screen? Okay, you have name 1. You have name, let me see, let me get your stuff on the screen so I can, okay, that's therefore. Name 3 just prints out the last line in the file without assuming that there are just 3 lines. Do this. Okay, so what you're going to do here, what you're going to do in name 3 is you open the file, right, that has the 3 lines in it. You're going to fseek to the end of the file. Seek is up. Fseek's the version of lseek, right? I think that's good. She uses fseek, right? And end of file is seek end. Okay. Once you've got, just listen and think about with you. So you've gotten to the end of the file, then you're going to have to lseek backwards until see, you might have, there's going to be a new line at the end of the file. So you want to go back past the last new line and then go and search for the new line before that, right? So you're going back and finding, not because there's a new line at the end of the file. So you go to maybe you go back to the end -1. So you're sitting on the new line at the end of the file. Then you search backwards in the file for the first new line. Now, then once the file cursor's there, you can just read forward using fscanf and print, because they're the place that if you can just like, I'm not sure, what does it say? What does it say to get the last line once you've gotten there? In it says, I think you use, then search backward a character time, then use get line. So what you're there, then you use get line, that reads the whole line into a buffer, and then you print it. Does that make sense? Okay, so you want to do that step by step.
With names, I would just like fix it.
So first you're gonna think about like let's write down the algorithm here. So what you'll do, this is name3.c, right? One, open names.txt, right? Two, seek to end of file. Okay, end of file -1 on last new line. Then seek back character by character, searching for a new line token. 4, you found the new line token, right? And so use get line to read in last line. 5, use, I think it's what is it? It's to, it just says a print. I think you can just use print, printf to print. But you have to read in last line to a buffer to print last line from the buffer. I think you can, does it use printf or maybe, what is the program, what does the text say? Is it F right? What is the one that you have? You have fscanf. I'm sorry, I can't hear. And then, but it doesn't say what to use to print it. Okay, so I think you can just use print F to print last line. So this is the outline for name 3, right? So basically, the character by character, this is going to be a while loop, right? So you'll have system call, while loop, where the you will be reading one character at a time, because you'll be doing, and what do you use to do a one character at a time? I think it is scanf, right? But you have to use that. But you have to use that in conjunction with fseek. It's like you're at the last thing, so you go, or you go back to, maybe you go back 2 characters, right? You're in the last character. You read that character, check if it's a new line. But then when you've read, your cursor's moved next. So you have to jump back to get the next character, check if it's a new line. But the cursors move forward once you have to jump back to get the next one. See, there's a leapfrog effect. Like, because for 3, let's say the text was ABC, new line, DEF, new line. Then the problem is you start here, S, right? But then you say you move but then let's say you've gotten past the new line. So you start here. Then you read, right? Do F scan F this F. But then what happens is then the cursor is on the last line, right? So you have to jump back, you have to move the cursor back to read the E, but then the cursor is there. So you have to, on the next line, you have to jump back to read, the cursor's there. That you have to, so you see, when you read, the cursor moves to the right, so you have to jump back to get the next letter. And eventually you'll find this new line, and then you call get line to get the whole thing. But you'll be writing that into a buffer, which is just an array. If that makes, does this make sense? Okay. Will, you have questions, or are you all set?
No, I'm just doing the diagrams. I do have a small question. So I noticed that you're asking for 5 diagrams, but there are 6 programs.
Well, yeah, one of them has the same. One of them is just
pretty much the same. Mystery 1A.
Well, one of them, it says don't draw a diagram, doesn't it?
Make a diagram.
Read the make a diagram instructions. I think there's 5 of them.
How mystery 1 works. Make a diagram. Terminates the screen, record any output you see on the screen on the data flow diagram. So both of those say so.
Because you read the text.
Oh, I am. I'm just.
I remember. Okay.
So here's the second.
Doesn't say one of them has a
mystery 0A. I don't need a data flow diagram, so I messed up there. I think it's prefaced with, here is a second program with the same data flow, so no need for a diagram.
No, there you are.
It technically isn't. It's slightly different, but
the program's different, but the data flow should be the same.
Well, one of them gets its contents from Hello 42, and the other one gets it from printf. So
the data flow is from the redirection isn't different. Yeah, the name, the which program is run, but they're different. I mean, they have the same redirection diagram. Not in terms of, the only thing that's different is stuff inside the program or the name of the program, right?
No. One of them has
well, maybe you have the wrong diagram.
Oh, okay. I guess it is the same, because Hello 42 is technically another program.
Yeah, and so you're running Hello 42, but it's in the process where you're writing, you're reading from, you're writing to file descriptor 1, right?
Yeah. Okay. Oh, that makes, okay. Never mind then. Thank you.
Yeah, you don't even need file descriptor. File descriptor 0 shouldn't be. You should erase. I don't think you need the line from file descriptor 0 either. Show your diagram again. Yeah, so you don't need, wait, why do you have, this is mystery 0? Why do you have 2? No one's doing anything with, Hello 42 is not a program. No, that's completely wrong. Hello 42, wait, mystery 0, there's no, it's not, that's the executable. It's not reading from file descriptor 2. So erase, first of all, erase the file with the Hello 42 on it. That's not part of the data flow. Mystery 0, go back to mystery 0. Okay, get rid of hello world in the file, because that's not a buffer. Get rid of the blue line to file descriptor 2 and the hello world in the thing below. Are you muted? Or maybe you can't hear me.
Oh, there. Sorry, I was muted. I need to use the facilities really quick. I'll be right back.
Okay.
But I'm gonna use this diagram here because it's closer.
Oh, I see what you mean. You're gonna.
Yeah. So sorry about. I don't know why it keeps muting me when I share my screen, but I'll be right back. Hey, buddy.
Oh.
Sorry if you heard me talking to my dog. You're still recording, by the way, Professor.
Oh my goodness.
So a little long,